conservation of energy and how to use the principle. I'm going to be discussing kinetic and potential energy, and I suggest that you take notes and try the problems as we go along, pausing to see if you can solve them without my help. Kinetic and potential energy. I will find that you already know the formulas for kinetic and potential energy. Kinetic energy is 1/2 mass times velocity squared, and potential energy for objects that are falling is mgh, where height is the height of the object. The potential energy that's lost often becomes kinetic energy that is gained. This is called the conservation of energy, this idea. Energy is conserved, such that the total energy is a constant in a system. The idea. Energy is conserved. But this is better described by the two energies combined are the same as they are later in total. That is, the initial kinetic energy and the initial potential energy add up to the final kinetic energy and the final potential energy. Now, I don't mean final as the end of the entire problem. I mean final after the process has taken place. Let's do an example. For example, imagine a roller coaster ride that is 12 meters tall, here and here. It's only 8 meters tall. Now at the top you might think that it has no velocity, but in this case I'm going to put in the unusual circumstance that this 20 kilogram cart has an initial velocity of 4 meters per second. Later on it will arrive down here with some new velocity that we don't know what it is, and that's what we want to find out. Let's use this idea. Kinetic energy initial is 1/2 times 20 times 4 squared, plus potential energy initial is 12. That's 20 mass times gravity times height. Mass times gravity times height. That's 20 times 10 times height. 12. Equals the later conditions, the final conditions. The final conditions are still 20 kilograms. It didn't lose mass or gain mass, hopefully, not like a rocket. So it's still 1/2 20 times velocity squared, but this time we don't know what the velocity is. But we do know the mgh. It's 20 times 10 times 8. 20 times 10 times 8. Can you see that? Beat me to the answer. So you should have got a velocity of 20.3 meters per second. Very nice. All right, here's another example. Imagine we're up on a mountain like this, and over here is a wall, but hooked to the wall is a spring, and we have various heights. This one is 6 meters off the ground, and this high mountain, and this high mountain is 22 meters up. Alright, very good, very nice. And up here we have a cart of 20 kilograms again, but this time it starts with an initial velocity of 16 meters per second. Our final question is not how fast is the cart going, but how much could it compress that spring? I'm going to have 3 parts to this and see if you can figure them all out. The first one is find the total energy of the system. So yeah, the total energy is a constant, so whatever it is, that's what it is. Well, that's mgh plus 1/2 mv squared. The total energy at any moment is the initial energy. The total energy at any moment is equal to the total energy initial. We're going to find the total energy initial, and we'll use that to solve for the total energy at any moment. All right, here we go. mgh, that's 20 times 10, 200, times 22, so that sounds like 4400 joules, plus 1/2 mv squared, that's half of 20, that's 10, times 16 squared, that's 256, and an O for the 10, which is that. There's your total energy, which appears to be 6,960 joules. Nice. All right, good job. For the next part, let's determine the velocity at 6 meters, right here. We can still use total energy goes to potential and kinetic, the two types of energy that we have at this moment. The total energy is still 6,960, but the potential energy is mgh, M20. M20 kilograms, G 10 meters per second squared, and H is 6, plus kinetic energy, 1/2 M20 V squared. 20 times 10 times 6 is 1,200, is it? Half of 20 is 10 V squared, and over here it's still this thing, 6,960. We can divide through by 10, and then the answer pops out immediately. V squared is 576, and we need to take the square root of both sides. So this velocity turns out to be the square root of 576, which everybody knows. Who's ever taken the square root of 576? It's a perfect square, and it's 24. Why didn't you know that? Anyways, now I'm going to use this kinetic energy to compress the spring, which has a spring constant of 200. We're going to compress it at distance x. Only this kinetic energy is necessary because we can't gain any more because the height doesn't change. Let's do it. Well, the total energy is a constant. It's still 6,960. But now there's three types of energy to worry about. We have potential energy, mgh. We have kinetic energy, 1/2 mv squared. And now we have spring potential energy as we compress the spring, so that's 1/2 kx squared, where k is the spring constant. In this case, it's 200. 6,960 joules, fine, it's a constant. It's the total energy. mgh is still 20 times 10 times 6, even when the spring is compressed at the final moment, final moment, final moment, final moment. The final kinetic energy is 0. It comes to a stop when it compresses the spring completely. So that's 0. But the final spring energy is not 0. The spring, 1/2 times 200, will be compressed a distance x squared, which we have to find. You'll recognize this once again being 1,200, and we can subtract it over here again and get 5,760. Over here, half of 200 is 100, x squared, and the 0, of course, goes away. So I subtracted that over here to get rid of it. Move the decimal 2 places, and get rid of that 100. So x is just the square root of 57.6, which everybody has memorized to be 7.6. So, to recap, you start up here with potential and kinetic energy. You go down here, and a lot of the potential becomes kinetic, so now we're moving faster. And then we're going to use just the kinetic to compress the spring. By the end of the compression, there is no kinetic energy left over, only potential energy. What would happen when the spring bounces back out? Can you imagine it? All of the spring potential energy gets turned back into kinetic energy, 24 meters per second, the reverse direction, and then up the hill it goes, back up here. Except this time, it's going to be moving backwards at 16 meters per second. Energy is conserved. What we haven't talked about is cases when energy is not conserved so well, cases like work done by friction, which is coming up